Class we were discussing about the governors, and in the end, when we were looking at the application of governors and the different types of governors that are used in different hydropower plants in India, then if you recall, we discussed that there is a particular category which is the micro hydropower plants less than 100 kilowatt, where actually the governor mechanism might not be really economical to implement because of the the complex control mechanism which is needed for the flow regulation and digital governor and all. So in such very small applications, the micro hydropower applications for controlling the frequency, there is another alternative which is sometimes used, which is known as the electronic load controller. So today we will just have a brief overview on this, few mechanisms and schematic of these systems. So as it says here, electronic load controller is a power electronic device used in place of conventional speed governor in small isolated micro hydropower plant for load frequency control. So the application is very limited. This is not really used widely, just only for these very small, less than 100 kilowatt typically isolated micro hydropower plant systems, usually in remote areas, hilly areas. So for them, actually, this ELC actually figures out to be more economical in terms as compared to the governor mechanism, the complex control which is needed for the governor mechanism. But by the way, as the control and the computational abilities are becoming more proliferant and they are becoming less expensive, so there is a fair chance, fair good deal of possibility that in the coming times, probably in governors of smaller sizes are also economical, then ELC can be ruled out completely. But as of now, there are ELC is still in practice. It is used in some of these remote, small micro hydropower plant installations. So as it says here, the MHP designers and planners have made their efforts to reduce the construction cost of MHP by using ELC instead of conventional oil pressure mechanical governor, or any of these hydraulic governors or the digital governors. So the idea, this is very interesting. What is happening is that now if there is a change in the load, so there are two ways. Is that one way what governor does is that it changes the input to the turbine. So the power which is being generated, that accordingly changes with respect to the load which is changing. Because basic idea behind any electrical power systems, I think everyone probably appreciates, is that storing electricity at a bulk size, in a megawatt scale, is not really economical as of now. The battery technology is not really up to the mark in that sense. So the whole challenge of power systems, a major component of the challenge is to balance the load and generation. And so this governor mechanism is basically nothing but one such mechanism which helps match the generation with the load on the system. So that is obviously the best way and is considered the standard way of doing it. But in this case, what we are saying is that for an ELC, instead of, probably it will not be really very suitable, not very economical to have a complex control mechanism for flow regulation. So in this case, what we are saying is that if the load is fluctuating, then instead of changing the generation we are not touching, generation we are just leaving as it is. Rather, we just play on the load side only, on the demand side only, and we adjust the load in such a way that the generation can continue at the same rate. So we don't vary the generation. We just play on the demand side, on the load side itself. And how it is done, as it says here, when there is a change in the system load, the frequency tends to change. In order to keep the frequency constant, the conventional speed governing system regulates the input water supply to the hydraulic turbine. So that is how the governor does. But in ELC, corresponding to reduction in system load, additional dummy loads are introduced to the system without making any changes to the prime mover. This makes the total load, which is dummy load plus the consumer loads in the system, constant, resulting in constant speed operation. This avoids the use of any flow regulating device and makes the scheme simple. So that's the basic principle. What is happening here is that we are not touching anything on the generation side. Rather, we are just introducing some dummy loads for for accounting for any load changes. So To put it here, I mean, for a governor mechanism, what we are doing is that you have a generator and then you have some loads which are attached to it. So if there is a fluctuation in these loads, then you accordingly change the power which is being generated. But in this ELC mechanism, what we are saying is that you have your generator, which is a small MHP generator, micro hydropower generator, and then you have loads. And now, if there is a fluctuation in the loads, what we do is that we just attach some dummy loads to this thing. So we don't touch the generating side at all. This keeps generating as it is. But these dummy loads, these can be introduced in the system if the actual load is going down. So ideally, how it would be done is that probably this whatever is the rated load of the system. So this generator accordingly can be sized so that even if it's a normal load operation, there is some dummy load in the system. So the generator can be slightly oversized that way. So you have some dummy load because in case if you want the control on both the sides. So if suppose you have some constant value of load, which is the rated value L0, and now if this load L0 decreases, then you want to add new dummy loads, which is possible. But suppose if this load is in some circumstances it is increasing from the base value, then probably you can take off some of the dummy loads and still supply that power. So there might be a need to slightly oversize this thing and along with some dummy loads. So these loads are what we are fluctuating in the system. So as it says here, to summarize, the basic concept any ELC uses is to let the turbine and generator run at their full power or possibly a manually set partial power and keep the electric load just right to attain the correct speed. So the entire adjustment is on the load side only, and the turbine generator is just running at its whatever is the speed which has been set. So that is the basic principle. I think that's quite simple. Any confusion or any question on that?
Sir, the dummy load is connected all the time or just we connect it when the load decreases?
Yeah, so as I said, see, it will depend upon what type of control you want to achieve. If you just want to have unidirectional control, that means the load as it is at its constant value, and when the load is dropping, then you don't want the frequency to increase. Then you can have no dummy load in the base case. But always it is recommended because load can fluctuate on either side. So ideally, it would be suggested in such a system that you should have some dummy load always in place, because in case if the load is increasing, then you can throw off some of the initial dummy load and still account for the frequency change. So better control will be there if you always have some dummy load in place. But then again, that will be, I mean, one argument against that goes is that you are wasting some power. Unnecessarily you are running those dummy loads. So, I mean, that is there because, and that's why you can see we are saying that this is only for micro hydro schemes, very small schemes where the power generation is not much and it's in a remote area. So you cannot really put a lot of power on the grid. Also, probably the grid connectivity is also not there. It's just a small microgrid type of thing, local area you're supplying. So maybe that dummy load can be, if it's in a remote or a hilly area, then probably it can be used for water heating or some such purpose. The dummy load can be a heating load. And because in mountainous regions, usually the hot water requirement is there. So that type of thing can be adjusted actually in terms of the dummy load.
Okay.
Anything else? Anyone? So let's move ahead now. So this basic concept is very simple. It's basically about adjusting the load using some dummy loads. So let's look at, there are three different mechanisms which are commonly used for this ELC system. So we'll look at these three mechanisms shortly. So the first one is the conventional form of ELC, electronic load controller, which uses, as it says here, it uses at least 3 sets of dummy loads and 3 sets of power electronic switches to dump power from each phase to the dummy loads. So this is what the schematic looks like for a conventional ELC. So you have your synchronous generator here, which is generating your power at frequency which is same as the standard frequency of the system, and you have a 3-phase power going out, and these are the loads here. So here, as you can see, there is a frequency sensing mechanism which you need, which is similar, which can be similar to a conventional governor thing this component here only, that basically you need to sense the frequency or the speed again. and then you sense it, and there's a reference value. The frequency has to be at 50 hertz. But if there is a change, then that error signal is given to a PI type controller or something of that sort. And then you have a, now here the difference comes. So there are, as you can see in this conventional thing, there are these three sets of dummy loads. Usually, I mean, as it says here, a dumped resistive load. So it can be a simple resistive load, which can, do the heating, heating coil sort of thing. So as I said many times in the mountainous regions, this is basically used for water heating. So the I square R loss, which will occur here, that will appear as heating. So the three dummy loads for each of the three phases, they are put here. And now you have the output of the PI controller is going to a gate signal generator. And why this gate signal generator is needed? Because basically you need to, control the power flow to these dummy loads. And that power flow is being controlled through these, power electronic switches, which can be thyristors or MOSFETs or IGBTs or any of these power electronic switches. So, so what will happen here is, in this case, is that the firing angle of these power electronic switches can be manipulated by the gate signal generator. So those from non-electrical background, I think I'll just explain it a little bit. So if you see, what is happening is that your generator, by default, what it generates is a probably close to an ideal sinusoidal waveform. So let's say this is the voltage waveform which is being generated by your synchronous generator. Okay, so that is the let's say the line voltage waveform here. Now what we are saying is that if there is a change in frequency, then let's say that the load has suddenly dropped and the frequency is tending to increase. So if the frequency is tending to increase, we need to increase the load so as to bring the frequency down. So to increase the frequency, to increase the load, what we'll do is that we will, this will be the error signal will come here, and through PI controller there will be a signal which will be given to the gate terminal of these power electronic switches. So what happens when you provide a signal at the gate terminal, these switches, they start conducting. So you can, for simplicity, sake of simplicity, you can imagine these things as like normal switches which can be put on and off, but instead of doing it manually, this is controlled by this signal generator. So this power electronic device has got three terminals. One of them is the gate terminal or the control terminal, where if you provide a signal of a particular magnitude, then it starts conducting. And if this signal is not there, then it doesn't conduct. This circuit is broken, you can say. So when you provide the gate signal, these power electronic devices, they start conducting. So basically, only one device is needed for conducting. So this one, the arrow here, whichever way the arrow is pointing is where it is conducting. So only one would be sufficient because you want a unidirectional flow of power only. You don't need a bidirectional flow. But for safety purpose, this other anti-parallel power electronic device is provided, so that if suppose by mistake, or in some malfunctioning case, there is a reverse voltage, then this power electronic switch doesn't get damaged. Rather, in that reverse voltage will conduct through the anti-parallel switch. So now what happens is that, as we said, now we want to control the power flow to these three dummy loads. So, and we can control that power flow by the time at which these switches, they start conducting. So what will happen is that, that is known as the firing pulses, or the the starting the gate pulses or the firing pulses for that power electronic device. So suppose if this type of waveform is being generated, and let's say let's say I want to put approximately 30% of the power. Let's say the load has dropped by 30%. So almost roughly around 30% or so, or 1/3 of the power I want to put on the dummy load. So what I'll do is that at a particular instant, that will be the mechanism of this PI controller and the gate signal generator that will decide at what point to fire these thyristor switches when it is to be put on. So let's say I want to remove 30% or 1/3 of the power. So somewhere here around this place, let's say I'll put on the thyristor switch. So what will happen that this much power now, this particular portion of the waveform, the voltage and the corresponding current, that will actually be conducted to these loads. So for each half cycle, accordingly, we can fire that thyristor at an appropriate time, like that. That will be going to the now that dummy load. So if you look at it, so this is the voltage which is being generated. So the voltage which will be fed to the load will be something like this now, going here, and then once you fire it, it just chops off, and then it goes like this. Again it chops off here and goes like this. Sorry. Yeah. So this portion, wherever it's cutting, that will be removed. So it's going like this, and this is gone. Then again it conducts here. So it conducts here. Again this one is gone, and then it conducts here, and this is gone. So the load will receive this type of waveform, and the dummy load will receive this type of whatever is the chopped off portion that will be fed to the dummy load, something like this, something like that. And now you can change this firing angle. At what particular instant you are firing in a given half wave, that can change. So if let's say you want to put 80% of the power to the dummy load, then probably you can fire somewhere here. So all this 80% of the waveform will go to the dummy load, and only remaining 20% will go to the main load. So that is the idea here, the basic concept. So this is the conventional form of ELC, which is known as the AC voltage controller based ELC. That is the name for this schematic, AC voltage controller based ELC. And so as we discussed, in this type of ELC, a dummy ballast load is connected in parallel with the consumer's load through a pair of anti-parallel connected thyristors. The power consumption by the dummy load is controlled by varying the firing angle alpha of the thyristor pair. So at which particular point you fire this particular thing, because this time can be equivalently converted into the angle, right? So this is pi radian, and this is another pi radian. So accordingly, the alpha can be decided depending on how much power you want to put on the dummy load. But as probably, people from electrical background can definitely appreciate, and for others also, if you see, this is a distorted waveform. This is not actually a sinusoidal waveform, especially for the load we are talking about. So this is a distorted waveform, and the amount of distortion will change depending upon the firing angle, but it will always be distorted. So if you resolve this, if you do the Fourier analysis of this, you will see there is a fundamental component, and then there are some harmonics or higher order components. So those things actually, there is a harmonic distortion in the voltage and current profile, which is not really desirable, and it produces a bad effect for the appliances also, which are connected at the user's end. So the major disadvantage here is that the harmonics introduced due to chopping of current through the ballast load, consumption of reactive power by the ballast load. So because whenever you have these harmonics, if you resolve them, you will see the power factor angle also actually drops. It's poorer. So that reactive power also comes into picture, and lack of current sensing mechanism and independent gate signal generation, which results in phase current imbalance, and thus generator oversizing is required. So we are not sensing the current at any point. We are just sensing the frequency. So there is a possibility, because this will be some loads which will be distributed across some residential area or some particular villages or all. So if there is an imbalance, that means some load is having, some phase is having higher load, another phase is having a lower load. So that thing is not accounted for. The firing angle is set same for all the three phases. So that current imbalance, if there is an imbalance system, that is not addressed here. So these are some of the major disadvantages. Harmonics is a major disadvantage in this case, because you are introducing a lot of harmonics by this type of a distorted waveform in the supply. So this is about the conventional system. Any question or comment on that?
Sir, this is Prasant, sir.
Yes, Prasant.
Sir, which type of switch used? Thyristor or MOSFET like IGBT?
So this here says thyristors, but as you probably understand, these days the power MOSFETs and IGBTs are more popular, and that also depends upon the voltage and current rating at which you want to operate. Ultimately, the power rating of the entire setup. So accordingly, a judicious thing can be chosen, but as we probably understand is that IGBTs and power MOSFETs are more popular.
More common. Yes, sir.
Okay, any other question, anyone? Okay, so So let's move ahead. So this was the first one, the simplest or the most common one, which is the AC voltage controller based ELC. But as we discussed, there are these major drawbacks, and these are really, very severe drawbacks actually, because if you look at the code of
Yes,
sorry.
sir, these micro hydro plants are used for isolated, used in isolation only, no, sir? Are they connected
Usually.
to the grid? No.
Usually it is difficult because they are in very isolated and remote areas. So usually they'll just form a microgrid and supply some villages around that particular area.
So in that case,
But
this is
but
possible.
that is just contingent on the grid availability, because if grid is available, they can then you can always have grid connection. But usually, I mean, the constraint is such that grid is not available, then you have that type of thing. Yeah, what you are saying?
This is it, sir. That micro hydro plants are generally used in isolated.
Right. So this is a major disadvantage, because if you look at the electricity supply code, what it says is the total harmonic distortion in your voltage or current waveform should not be more than 5% typically. So, and this type of mechanism, when you're having, you have a very significant harmonic distortion which will be coming into picture. So not really a very advisable way or good way of doing this. So that's why people have come up with some other mechanisms also. So another one, which is known as the discrete resistance type ELC, is having a slight modification. This is also very popular. This type of ELC turns on or off the discrete resistance bank rather than chopping the voltage across the dump load to increase or decrease the power consumed by the dump load. So this is the mechanism here now. So now in this case, as you see, what we are doing is that for each phase, so this is for phase A, this is for phase B, it's not shown here, just the box is there, and same with for phase C. So in phase A, if you look at it, you have n number of dummy loads, and 1, 2, and so on up to n. And each dummy load is controlled by, again, that type of a anti-parallel thyristor or any particular power electronic device mechanism. So now what we can do is that instead of chopping the voltage or current like what we were doing earlier, that we are firing the thyristor in between and doing this. So instead of that, what we do is that we decide that for a given power level, how much dummy load we need. Accordingly, out of these n, how many of these dummy loads need to be in the circuit, how many of them need to draw the power. And whichever is drawing the power, they will draw the power for the entire cycle. So the firing angle will always be 0 degree, alpha will always be 0 here, but only choice will be that which of these need to be fired, and that choice will depend upon that how much is the dummy load you need to introduce in the system. So this side is still same, this says here P controller, but typically PI is the most common one because PID is slightly more complex and P will have an offset, so typically this should be a PI controller. And then same gate signal generator. So the difference now is that we are not varying the alpha or the firing angle, that is just 0 degree. Only thing is that which all different thyristors are to be fired, that is what the control mechanism decides here. So this is an advantage over the previous one, as you can understand, is that now this problem of harmonics has been removed. So you only have, there is no chopping of the voltage or current waveforms. So the waveform is entire, going in entirety. Only thing is that some of these will draw some particular power. And that is a better thing, but the problem here is that now, as you can understand, this discrete resistances, so how many of these resistances to have and what different values you should have so that you can cover all the possible combinations of the loads, that is actually a challenge. So having that discrete resistance bank, you need to have a bank of resistances. So that is actually the challenge in this case. So major drawback of this ELC is the requirement of discrete sizes of dummy loads, large number of dummy loads, and high cost associated with them. So as you can understand now, the cost will basically increase because there you had only just one size dummy load, whereas now you'll have to have different sizes of dummy loads for each phase. So this the cost will be higher, and also the space requirement or other things will be more demanding in that sense. So that is the problem with this discrete resistance type dummy load. Any questions on this? So let's move ahead. So this is the second one. And the last one, the third one, it basically tries to improvise upon both of these and their shortcomings. That is not really very popular, but is being proposed in terms of a better mechanism which can be possible. So this is a newer variant, not really popular. Both of these, as you can see, these are widely used. This is discrete resistance type and also the AC voltage controller type. But a new proposed one is basically the microcontroller based ELC. And as you can understand, microcontrollers are they are better in terms of the technology and upgrade you can think of. But the idea is that they have been not really very popular conventionally, but with increasing availability and dropping cost, this will be probably more preferred. So in this case, what is happening is if you look at the diagram here, this is the schematic. So as it says here, a set of diodes forms the half-wave rectifier circuit. So you have a three-phase rectifier, which can be a half-wave rectifier in this case, as it says. So you have a three-phase rectifier here. So you are converting your given AC voltage to an equivalent DC voltage, DC waveform. And the dummy load is connected at the DC bus marked A. So your dummy load is connected at this DC bus. So this is your dummy load here, this resistance which you are having here. As I said here, the single ballast load. And then you have a IGBT switch. So this specifically, as it says here, has to be a high duty IGBT switch. And the rectifiers can be of different power electronic devices, but this typically IGBT due to their ability to operate under different circumstances and better response. This is recommended as IGBT switch. And now what happens here is that an IGBT switch completes the circuit by connecting the other end of the dummy load to the generator neutral, which is grounded. So this is one end is going to the neutral, but the gate signal to this IGBT when it will conduct, that is coming from this microcontroller. And because you are using a microcontroller which can have different inputs and also have a computational capability with it, so now instead of just frequency sensing, we can do voltage sensing and current sensing through some CT or PT. So this is actually a significant advantage. As you can see, it is covering all the disadvantages. It is not having the chopping of this particular thing, like the waveform chopping is not there. It is also having current sensors to account for any imbalance in the phases. And also the need of discrete resistance banks has been ruled out. There is just one single ballast load. And how it will operate now is that the frequency sensor will be the primary trigger for this. So frequency sensor, it senses if there is a change in frequency, and that particular is the basic trigger. So if there is a change in frequency or shift in frequency observed, then this will provide a gate signal to the IGBT. So the IGBT starts conducting. So through this three-phase rectifier, equivalent DC comes here and is going to the dummy load. And the voltage and the current sensor, they are needed for that imbalance thing. As we said earlier, is that earlier we didn't have any current sensing mechanism, so there was an imbalance, which is the conventional system and also the discrete resistance type system. So to avoid that, now because you have a microcontroller, that thing is very simple. You just have already have CTs and PTs in the power plant, and you just connect their input to the microcontroller, and the microcontroller can be programmed to accordingly sense that if there is an imbalance, so accordingly the amount of this particular the gate signal here can be varied, and this thing actually would be having a much better functionality. So the main feature of the proposed scheme of ELC is the ability to draw different currents through different phases of the AC side of the rectifier terminals. So basically what will happen here is that, that is not shown here through a link. Basically you can understand, and also in the block diagram also we can have a conceptual thing. So this will have a control mechanism for these three-phase rectifiers as well. So idea is that whenever you are having a imbalance, phase imbalance, which is being sensed through the voltage and the current sensors, then what it will do is that one thing is that this gate signal will be generated depending upon the frequency sensor output. But the firing pulses for these three-phase rectifier switches, that will depend upon this voltage and current sensor. So if you have an imbalance and some particular phase the load is higher, some other phase it is lower, so accordingly the timing or the firing pulse of these different three phases can be different. So, the power which is being drawn from the different phases can be changed. It need not be the same power from all the three phases. So that is one very interesting and advanced capability which it can come with. So accordingly, as it says here, it is the ability to draw different currents through different phases of the AC side of the rectifier terminals, which allows it to compensate for the unbalanced consumer currents. So that way it is the most advanced type of ELC, but not really very popular as of now. But hopefully with advances in the computational abilities and drop in the prices, probably this will be more popular that way. So this is the microcontroller based ELC, which is the best one, the state of the art, you can see. So any questions on this?
Sir, this is Prashant.
Yes, Prashant.
Sir, it is using only one dummy load.
Right.
Is this in disadvantage?
No, not really, Prashant, because basically we want to have some particular, power which needs to be consumed here. So the power consumed will be I square R, right? So resistance can be chosen appropriately, and but the current can always be manipulated, right? So that won't be really a very big constraint per se, because you already have control for the current which you need to draw from the different phases.
Okay.
Yeah.
We are changing the overall power, and that is the
Right. Very correct. So how much power you need to put, you need to make flow through the dummy load, that is controlled by the current, firing pulses of these three-phase rectifiers. So with only one ballast load also, this can actually have a range of dummy load operations.
So, sir, in any type of ELC, there will be a dummy load in always. There will be a dummy load,
Very correct.
every time it will consume some power, and that is the you can say that minimum one of the disadvantages you can tell of ELC in ELC.
That's true. That's true. That is actually part and parcel. That is how the ELC is being defined. That you always need to have a dummy load here. So there will always be a power loss. So probably what, as I was saying earlier, also is that a practical way of implementing can be that if you have some sort of power requirement which is always there, like I said about the hot water requirement in mountainous regions. So those things can be probably coupled. Those type of demands can be met through this particular aspect. So, and as you see here in the conventional one, we had one dummy load for each phase, and this one for the discrete resistance type, there are a lot of dummy loads for each phase. This is actually best that way, that you just need to have one single ballast load. So that way it is optimal also. And yeah, that power loss will always, I mean, that is the concept only, that you don't change the generation, you change the load. So some power by definition you are going to waste actually, so to say. So, but only good advantage can be that if you can find a utilization or a useful application for that dummy load, then actually the entire system efficiency would be better.
Yes.
Something of, you can think of it like a combined heat and power plant, CHP. So which is very common in industry, process industry and all. You always, because you need steam also, or your process heater is also needed for a lot of functions, and you need electricity also. So it is something on those lines, that this whatever is the waste power that can be used for heating or some other such application, and the main power is the power for the loads.
Yes.
Sir,
Yes.
Pranit, yeah.
Yes,
Sir, which one is normally used out of these three?
Yeah, so as we said, these first two are more common. The microcontroller based systems are not really common, and the conventional one, that means the AC voltage controller type, and the discrete resistance type are more common. By the way, from some practical experience, I recently, around the beginning of 2020, I visited this Arunachal Pradesh, and there was some seminar sort of thing with the Department of Hydropower in Arunachal Pradesh. So we had some interactions with the different executive engineers and superintending engineers in Arunachal Pradesh Power Department. So they actually have a lot of these ELC type systems, but they were saying that the on-ground performance is not really good. So they were not really happy that way with the existing ELC systems, and there is a lot of problem of breakdown and such things they keep encountering. So probably these existing systems are not really functioning that good on ground, and that might also be thing, or I mean an impetus for going to the better and advanced systems. And also technology wise, as you can see, it has got many inherent advantages. Okay, so but as of now, these first two, the AC voltage controller type and discrete resistance type, are more common.
Okay, sir.
Does that answer your question, Pranit?
Yes, sir.
And anyone else? Any other questions or doubts? Okay, so I think if there is no doubt, we'll just stop here, because this was all to be discussed in ELC. And
Sir, hello sir.
yes, Anvesh.
Yes sir, how that frequency is related to the three factors of the controller and all?
In the microcontroller one?
Yes sir, in microcontroller, how the frequency sensor works?
Yeah, so see here, these are two different sets of controllers, and as I said, the frequency sensor can be, I mean, it can be achieved to any of those different sensors which are used even for normal governor operation also. But the idea would be that frequency sensor will tell you that how much is the frequency, whether it is 50 hertz or if there is a fluctuation up or down. So whenever there is a frequency variation from this will give an error signal, and this error signal, what it will do is that it will produce, the microcontroller will analyze this error signal, and accordingly it will introduce an appropriate time gate signal for the IGBT. Okay, so because this IGBT, this device, this is how it conducts, is that whenever there is a gate signal applied, this is the gate terminal. So whenever there is a gate signal applied, then only it conducts. So how much power, for how much duration and what current you need to draw. So one thing is that for how much duration you need to draw. So that particular thing is here, and also how much current you need to draw. So for that comes into picture the voltage and the current sensors. So the voltage and current sensors can be your typical PT. So voltage can be sensed through a potential transformer and current through a current transformer. And this actually, why we are doing here is that because we want to detect any imbalance in the phases. So you have three-phase system. So there is some VA or corresponding current, IA, IB, and IC. Now there is a possibility that the magnitude of one of these is lesser than the others. So this is what an imbalance system would look like. And we don't want to have this type of imbalance, because that creates complexity in the operation of the system. So what it will do is that these voltage and current sensors, they will give that information, that how much is the the current in each phase, and accordingly now this particular input again will be fed to the microcontroller, and that particular output, I mean based on the control mechanism implemented through the program here, what it will do is that it will control the firing pulses for the three-phase rectifier. So this three-phase rectifier here, because that is what will decide how much current will come from the main line to the dummy load. So together these two, if you see, if you combine them together, how much current will flow and for how much duration it should flow. So accordingly, that will determine how much power is to be drawn. So that is how frequency sensor is what actuates the entire behavior. Only when there is a change in the frequency, there is a deviation in the frequency, only then we need this operation of this entire path. So frequency sensor will actuate the path, the entire operation, and voltage and current sensors will tell you whether the system is balanced or not, and if there is an imbalance, then accordingly how much current needs to be drawn from each phase. So that way, accordingly, we can decide upon how much power will be drawn from the, will flow to the your ballast or the dummy load. Okay.
Yes sir, understood sir. Sir, but that IGBT MOSFET, these are very heavy term for me, sir.
Don't be afraid about it. We will not go into the, the operation of the machine itself, or of the device itself. So these are power electronic devices, and you can, for simplicity, for our purpose, you can just imagine them or conceptually understand them as switches basically. and they are just switches which are there are also, in fact, technically also many times they are referred to as power electronic switches or power electronic devices. So only difference is that these are not manual switches like you have to put it on or off by your manual action. Rather, they are controlled automatically through the gate signal or the firing pulses. So it's only that it's like this is a switch here. You can think of it as a switch. So when you don't provide a signal here, then the switch is open. The circuit is open. The switch is off. So there is no conducting path available here. But when you give a gate signal, then this switch goes from off to on mode. And when the switch is on, the circuit is complete, the path is complete, right? So the current will flow through this. So for conceptual understanding, this is how we need to understand the switch. The power electronic devices, the IGBT or MOSFET is just a switch, and they have long names. So this is the insulated gate bipolar transistor. Then you have the metal oxide semiconductor field effect transistor, that is MOSFET. So those are basically different technologies. How that switch has been physically implemented. What is the type of circuitry which is inside? What type of electronic devices have been used? So, and why we have different varieties, like thyristors are the most simplest one, the simplest ones available. Then you have GTO and gate turn-off thyristors. Then you have the MOSFETs and IGBTs, different varieties. So why those are there is like the same reason why you went from 8086 type processor to Pentium, then to XP or whatever the better and advanced computers. So the idea is that you need to have in thyristors or in power electronic switches, basically what you want to improve 2-3 things. One is the ability of their the voltage and current carrying capacity, the operating voltage and current, the power handling capacity, and also you want to improve the switching speed. So because in this case, when we are talking about switching speed for power electronic switches, so that will be in kilohertz or megahertz type of frequency range. So very fast switching is probably desirable for most of the applications. So the switching speed needs to improve, the power and the current capability needs to improve. So due to that, different new devices keep on coming. People keep on doing research on that and come up with new devices. So I think that type of understanding is okay for this course.
Yes, sir. No worries.
Okay, anything else? Okay, so then we will stop here for this class. This is all for ELC, and next class we will start with the, maybe a couple of classes probably we'll need for the excitation control, 1 or 2 classes, and then we'll go for power factor control. So all this I think we will be able to complete before the mid-sem break.